Hello, my name is Dr. El-Bahrawy. I'm Professor of Hydraulics at the Faculty of Engineering in Shams University. Our lecture today is titled Optimal Design of Water Supply Pipe Systems. We are going to use optimization methods for the optimal design of water supply pipe systems. But before doing that, it's important to understand the basic hydraulic and economic concepts. We are going to give several examples to demonstrate the use of optimization methods. For most calculations, except for the last examples, we are going to use spreadsheets for calculations. Pipe-pump trade-off. The first example is called the Thurstville problem. Design calculations is taken from a book by Alan Smith et al., published in 1983. This slide shows the layout where we have a reservoir and we have to transmit water through a pipe and a pump to a city where they have a storage reservoir to accommodate for the variation in demand. If we look at the problem, we distinguish between 5 different variables. For the trunk main, the discharge, the diameter, and the head loss, in addition to the storage volume in the tank and the pump horsepower. These variables have interrelations that are expressed in 3 equations. One of them relates the head loss HF to the discharge Q, and the second one relates horsepower HP to discharge and head loss. The third equation is to calculate the volume of the floating reservoir from the demand curve as the cross-hatched area, which is the volume of water above Q average during the hours of maximum discharge. Out of the 5 variables, Q, D, HF, HP, and V, only 2 variables are independent, D and Q. The other 3 variables, HF, HP, and V, are dependent and can be calculated from Q and D. The total cost of the system is the sum of the cost of pipe in equation 4, the cost of reservoir in equation 5, and the cost of pump in equation 6. The algorithm used to the total cost calculation starts by choosing a value for D to calculate the cost of the pipe, a value for Q to calculate the head loss and horsepower to calculate the cost of the pump, and from the demand curve we calculate the reservoir volume and its cost. The total cost is the sum of the costs of pipe, pump, and reservoir. A long time ago, in the early 70s, before the invention of calculators or computers, we used charts to calculate head loss, horsepower, and reservoir volume and the corresponding costs. We entered values for Q and D, as shown in the slide, and work out the hydraulic and cost calculations. This is a contour map of the isocost lines showing the domain of all possible combination of discharge and diameter, from which we can see 2 values for minimum cost. One of them is a local minimum and the other is a global minimum. The global optimal solution has a cost of 1,009,068 monetary units with optimal diameter 0.408 meter and optimal discharge of 0.35 cubic meters per second. Optimization by enumeration. Enumeration means that we calculate all the feasible combinations of Q and D in the whole domain and choose the minimum one. This Fortran program has 2 nested do loops to try 50 values of Q and 50 values of D to calculate total cost for 2,500 combinations. For each combination, we conduct hydraulic and cost calculations. After the do loop, we compare the calculated costs with the previous one to choose the smaller value. At the end, we obtain the minimum cost and corresponding optimal values for Q and D. Now, in this slide, we use the spreadsheet to repeat the calculations for a chosen combination of Q and D. The spreadsheet is divided into sections for input data, demand curve, design and cost calculations. The output of the spreadsheet model is the total cost of the system. In this slide, we use spreadsheet to repeat the calculation in the previous slide for all possible feasible combinations of Q and D. Using data, what-if analysis, data table, we can create a two-dimensional table with values for diameter in the top row and values for discharge in the left column, and highlight the range for cost calculations. Here, in the data table window, we define the row input cell diameter and the column input cell discharge and press OK to fill the table with total cost values. We can then spot the minimum cost and the corresponding optimal values for diameter and discharge. The minimum cost is 1,000 and 10,000 monetary units, and the optimal values of D is 0.4 meter and for Q is 0.35 cubic meters per second. The optimization model, the previous calculations can be put as a nonlinear optimization program to minimize the objective function Z for total cost of pipe, pump and reservoir, subject to a set of equality constraints for head loss, horsepower and volume calculation, in addition to a set of limits on diameter and discharge. Nonlinear programming. This spreadsheet model shows how to use the solver to calculate the minimum cost of the system expressed in the previous mathematical model. The same model used before can be used to define the solver parameters. Set the objective function to minimum by changing the variable cells for diameter and discharge, subject to the constraint setting upper and lower limits for discharge represented by Q max and Q average respectively. The starting point was D equals 0.4 meter, Q equals 0.35 cubic meters per second, with a total cost of 1,124,000. Using the GRG nonlinear solving method, the optimal solution is found with minimum cost of 1,009,000 and optimal values for D is 0.408 and Q is 0.305, which are the same values obtained from the isocost contour map shown before. This is an enlarged snapshot of the workbook for the nonlinear programming solution. Irrigation pipe networks. We move now to a different type of problem for irrigation pipe networks, where we have a source of water that supplies flow through 2 pumps and 10 pipes to 5 terminal nodes for sprinkler irrigation. System variables are discharged through pipes and head at terminal nodes. Only 2 equations are used, one for velocity and the other for head loss as shown in this slide. Calculation of terminal node heads is also demonstrated for node number 5, where we follow the path from the source to the terminal node passing by the 2 pumps and pipes number 1 through 5. For system layout, constraints and cost, this slide shows the flow needed at the terminal node, 4 cubic feet per second, and the system constraints for an upper limit on velocity 6 feet per second and a lower limit on the terminal nodal head 580 feet. The total cost of the system is calculated as the cost of pipes and pumps expressed as a linear function of both diameter and horsepower respectively. The spreadsheet shown for the trial and error solution is divided as before into sections for input data and design calculation, in addition to a section for terminal node calculation and a table of available discrete diameters and pump heads. Then we go to the trial and error solution that starts by selecting pipe diameters and pump heads from the table, and the model calculates pipe velocity and terminal node heads. Conditional formatting in Excel is used to show velocities and heads violating the constraints, so the designer change the values of diameters and pump heads to satisfy the constraints as shown. The slide shows an infeasible solution that violates velocity and nodal head constraints with a total cost of 49,000 monetary units. In this slide, solver is used again for solving the nonlinear model using the previous slide as a starting point and the GRG nonlinear solution method. The solver parameters minimizes the total cost, changing the variable for pump heads and pipe diameters with constraints on upper values for velocity and lower values for nodal heads. The optimal solution obtained found a total cost of 51,047 and optimal values for pump heads and pipe diameters. Optimal pipe diameters are not discrete and not included in the table of available diameters. This is an enlarged snapshot of the workbook for the nonlinear programming solution. The discretization problem. This slide rounds obtained continuous diameters into available discrete values from the table to satisfy the constraints. The obtained discrete solution has a total cost of 55,000. It can be seen that total cost value is larger than that of the continuous solution obtained in the previous slide. The linear model. We use here a hydraulic and mathematical trick to convert the highly nonlinear problem into a linear one by dividing each pipe into 3 sections of different lengths, each have a diameter that satisfies the velocity and terminal node heads constraints. By doing that, we replace the system variable from nonlinear pipe diameters into linear pipe length at the expense of increasing the number of system variables. If we choose 3 candidate diameters, the number of system variables will be 30 instead of 10. This slide shows how we write the head loss equations in terms of the linear pipe segments lengths. This slide shows the total energy line for the pipe with 3 segment lengths after replacing the diameter D with the candidate diameter length Li, where I changes from 1 to 3. Linear programming. The spreadsheet now contains more design variables as mentioned before. The advantage of using linearization of the problem is that the obtained solution by the simplex method guarantees an optimal solution. The solver window now contains new objective function and set of system variables 2 plus 30 subject to constraints for an upper limit to pump heads from the table, lower limit for the nodal heads as before, in addition to a new constraint that the total length of candidate pipe lengths for each pipe should be equal to the length of the pipe, which is 3,000 feet. Here we use the simplex LP solution method. For linear programming, we don't need a starting point, but I used an arbitrary constant candidate length of 1000 foot for all 10 pipes. This slide shows the obtained linear programming solution with a total cost of $54,143, a value that is more than the nonlinear solution and less than the discrete one. It can be seen that the optimal solution didn't use all the candidate diameters, where for most pipe, 7 out of 10, only one diameter is used. This is an enlarged snapshot of the workbook for the linear programming solution. In this slide, I compared the solutions for the irrigation system examples to include the computational trials, starting with the trial and error and ending with the linear programming solution. Water distribution networks. This illustrative example introduces a water supply distribution network that includes closed loops with different network components like reservoirs, pumps, pressure-reducing valve, and other valves. This optimization problem is a bit complicated. The formulation shown minimizes the cost of pipes and pumps, subject to a set of nonlinear and linear constraints for the loop and continuity equations, in addition to a set of limits on design variables. The last three equations, 8 to 10, shows the calculation of friction and minor losses as well as head of pump in terms of the shutoff head H naught. To perform this sophisticated nonlinear programming model, we have to define the network through a set of standard data comprising 5 groups records as shown in this slide. This slide shows the standard data for the illustrative network example. This is the starting point for the nonlinear programming model using the package called minus, which is the same package used in Excel under GRG nonlinear. Using this starting point, the optimization model solves for a continuous solution where the values of diameters are not discrete, and the total cost is much less than that of the starting point. The discretization problem. Since the obtained continuous solution is of little practical value, we need to find an optimal discrete solution. Such solution can be obtained using a completely different optimization method like dynamic programming or mixed integer programming, or we use indirect solutions by rounding the continuous variables from the linear and nonlinear models. The rounding procedure should not violate the constraints. To facilitate the rounding procedure, we may make the constraints soft to allow some acceptable violation within certain limits. This slide shows the banana function where the optimal discrete solution is not the next lower and upper discrete values of the continuous solution. This may demonstrate the difficulties that may arise when dealing with nonlinear cost functions. A simple example here is given to show how to examine the discrete values around the obtained continuous solution for a simple two-pipe network with pumps. This slide of the solution tree and an illustrative graph shows the 4 discrete solutions that we use to find the minimum discrete combination of diameters of the 2 pipes. In this lecture, we used a simple method suggested by the author to facilitate the discretization procedure by a simple cost comparison between the nearest discrete values for each pipe as a result of diameter and pump shutoff head modifications to satisfy the constraints. The following 2 slides show the modification to the total energy lines for cost-based calculations. The first slide shows the total energy line for the next upper and lower values of diameter for a simple pipe without a booster pump. The second slide shows total energy line for the next upper and lower values of diameter for a single pipe with a booster pump. This illustrative example is used to demonstrate suggested cost-based analysis to obtain a discrete solution. English units are used in this network layout. Since the solution is obtained in SI units, this slide converts the English units in the previous slide. Using the same nonlinear model shown before, this table shows the optimal solutions obtained before discretization. This table performs a cost-based calculation to decide which next discrete solution is selected for each pipe. This table shows the optimal discrete solution based on the table shown in the previous slide. You can notice the increase in total cost because of the discretization procedure. This concluding slide shows the importance of the different optimization techniques to find the optimal design of several water supply systems used here. Such solution depends on good understanding of hydraulic and economic concepts. The last paragraph showed that the spreadsheets can be used efficiently to solve simple water and irrigation systems. I hope you enjoyed my lecture. I tried to cover some difficult material by simplifying the concepts and the calculation processes.